Chapter 11 and 6. This chapter is power factor. In Korean, it's 영률. Power factor is very important, the concept, to describe the power and to distinguish the active power and reactive power and apparent power. Actually, we have H power here. Some impedance. So we call this V, this is I, the current. And say Vt is Vm cosine omega t plus zeta V. Zeta V is a phase angle of the voltage. And current is Im cosine omega t plus zeta I. The zeta I is a phase angle of current. This is a very general form of AC source. Then the power, the time, the instantaneous power Pt can be written this way: half Vm Im cosine zeta V minus zeta I plus half Vm Im sine 2 omega t plus zeta V plus zeta I. This is the instantaneous power. And the complex power can be written here, will be the pager of when you describe the voltage and current in the peak values, and there will be half Vi conjugate. So it can be written half Vm Im cosine zeta V minus zeta I plus J half Vm Im sine zeta V minus zeta I. We call this is active power and P, and this is a reactive power, Q. So active power is the same weight, average power, and this term and this term. This is average power. So, and we have the magnitude of the complex power. We call this apparent power. In Korean, is 피상전력. Is 1/2 Vm Im. In Korean, this is a 피상전력. In Korean, this is apparent power. In Korean, 피상전력. Actually, we have a source here, and the long line here, and this is a load. Through this, the transmission line, this is a transmission line. This is a actually, the power flowing through this transmission line is apparent power. But the really active power can be consumed to this load is active power. In the viewpoint of transmission line, the transmission line deliver the power is the apparent power. but the effective power is only active power P. So in the viewpoint of the transmission line, we want to know how much effective the power is delivered through this transmission line. So we want to define the power factor. Defined in this way. The apparent power and active power. This showed how efficient the power is delivered through this transmission line. We call this is a power factor. For example, if the power factor is 0, that means there are many power flowing through this line, but the active power is 0. There is no power delivered in the really. So power factor, the maximum power, so that will be written here is Vm Im. The active power is like that. So half Im V minus Zi. Let's delete it in this way. So it will be cosine W minus Zi. We represent the power factor as PF. Know that these values, zeta V and zeta I, mean phase angle difference. Between voltage and current. We call this is a impedance angle. When impedance phase, we call this as load angle. So, because that is determined by load, not by source. So power factor is determined by the load. Power factor cannot be determined by source. Power factor, therefore, so this is very important. So active power can be present in the way is half Vm Im and power factor. For example, let's say the power factor is 0.8. What's the meaning of that? That means cosine zeta V minus zeta I is 0.8. From here, we got it will be 36 and a 7 degree. The cosine is an even function. So to satisfy this power factor, there are two, the load angle. Here, zeta V minus zeta I can be 36.97 degree, or it could be minus 36 and 98 degree. Why? Because cosine is even function. So when you say theta v and theta I is positive, and we call this is current. Is lagged by voltage. Or if theta v minus theta I is negative, then we call that is a current is leading in voltage. Now I will call later. Actually, exactly this can be represented in the lagging power. Exactly, this is a leading power. And current lagged voltage. And voltage, in this case, the voltage and current lead voltage. This is important, the word in the lagging power and leading power. Now what is the lagging and leading mean? Here, you say the laggings when the voltage is represented in this way. This is a voltage. The current is looks like that. And this is lagging. I mean, current is lagging. This is lagging power. But when the voltage is like that, then current is like that. The phase angle is advanced to the voltage. When this is a current, and this is a voltage, and I'm sorry, I'm long. This is a voltage. Current looks like that. This is current. Then this is a leading power. So we will later discuss about here what happens when the inductor power or capacitor power, the viewpoint of the power, okay, the first case is capacitive. Load. This is capacitor. There are source here. So this is Vm and 0, and the impedance is j omega c, 1 over j omega c. Then what is the current? Current I is V over G, so there will be Vm 0 and minus j 1 over omega c. There will be Vm 0 and this is a 1 over omega c, and angle is minus 9 degree. So there will be omega c Vm and angle is 90 degree. So what's the meaning of that? In this case, theta V is 0, but theta I is 90 degree. Therefore, theta V minus theta I is negative. The current reading. So when the capacitive load, the power is the leading power. So the power, that will be Vm Im cosine that here, but the P is theta V minus theta I. That will be 0. Therefore, power factor will be cosine theta V minus theta I is 0. But in the case, what's the meaning of that? In this, the Q is half Vm Im sine theta V minus theta I. So it'll be, because this value, this load angle is minus 9 degree, there will be minus 0, minus 1, half So what's the meaning of that? When all apparent power can be transferred through the reactive power. So active power is 0, therefore power factor is 0. So but this power is especially called the leading power. Right? The current phase is lead the voltage phase angle. So the capacitor leading cause leading power. But how about the inductor? Inductive load. So say this is source, inductor here. Okay, this is Vm 0 degree and J omega L. Then current I is V divided by Z. So Vm 0 J omega L in Vm omega L, and angle is minus 9 degree. So in this case, theta V is 0, but theta I is minus 9 degree. Therefore, theta v minus theta I is positive. So that means current lagging. So in this case, apparent power is same thing, Vm Im. This is Im. But the power is half Vm Im cosine theta v minus theta I. That is 0. Why? This is a 90 degree. Therefore, power factor is cosine theta v minus theta I is also 0. But in that case, the reactive power, the Q, is half Vm Im sine theta v minus theta I. In this case, that value is 90 degree. Therefore, this is 1, so there will be half Vm Im. This is the reactive power. But this is a positive. So when it's inductor case, makes the lagging power. In Korean, the leading power in Korean is 진상 전력. In Korean, the leading power is 치상 전력. Therefore, capacitor is a leading element, and the inductor is a lagging element. So it's quite simple, but it's very important. So why we deal with this power factor? Because the power factor is very important when the power transfer. I will give you an example. Power factor is very important to deliver power. For example, this is a simple example here. This is a generator or generator station here, and there are some lines, here, and there are the load. It could be a resistive, capacitive, inductive, whatever it is. So anyway, generally the load is inductive. So that means there are some resistor and inductor in this way here. And generally, the load is inductive. The R and L. So to transfer the power, the grid corporation, such like the Hanjang, make the transmission line. So it's a very huge lines. So this is conductors. So we can make a resistor. Because long lines, it could be modeled into inductor here. So this is a return path, the symmetry, so they look like that. So we say this is a transmission line. And this is load. So we define this as R1 over half and L1 half in this way here. The target is to deliver the power to the load. So we need to make this voltage is exactly Vt. The Vm zeta V. Even though this is Vs, is an A angle 0. So the load require the load requires the terminal voltage of load. That means load require Vt, not Vs. The load don't care about what is Vs. They need only exactly 220 volt of our outlet. So this voltage is important. Therefore, the grid corporation needed to provide the very good quality voltage 220 volts at this point. So this is a concern about that. And the loss, this is a loss. The power line, because of this register in R1 make a transmission loss. So we need to minimize this transmission loss. But we know that R1 and L1 is a fixed parameters. Why? Because this is caused by the transmission lines. So this is fixed. In the same way, we cannot change. Vm is fixed variable. Why? Our load require to gather Vm at 220 volts. So in the viewpoint of the transmission line operator, such as the Hanjang, the Capco in Korean, in English Capco, need to minimize the power loss caused by this transmission line. The Capco wanted to minimize this transmission loss. How can you do that? That is related to the power factor. I mean, actually, in the load, need to pay the cost, the active power, not reactive power. So, in the Capco, such like transmission line operator, need to transfer only the active power to the load. If there are there are much other powers, such like the reactive power, because reactive power makes current. The current generates the transmission loss through this R1. So the power factor should be higher as much as possible, because higher power factor minimize the transmission loss. So G line, we define the G line can be modeled as R1 plus J omega L1. So the active power consumed by the transmission line, the power line will be square of in real G line. So it will be R1. This is average power of of the transmission line. Actually, the P is contributed. I mean, we said their power loss is a P. Then P is fixed, and VM is fixed. P and VM are fixed values. This is a given. That means this is a given values. This is not variable in the viewpoint of the grid operator. So the power is VM, IM, and power factor. So that means the current magnitude is P and VM and power factor. So we adding here that variable there. So what is the lowest power line? Line is half IM square R1. R1 is given. VM power factor 2P square R1. So we need to see in detail the power line loss. R1 is fixed and P is fixed. Why? This is required load, and VM is fixed. The only variable we can minimize the power line is the power factor. So increase power factor can make power line, the loss, minimized, reduced. So the grid operator, right, the Hanjan, require to maximize the power factor to the load. Because the power factor is the power factor is defined in this way here, and S is a P plus JQ. Therefore, the range of P power factor is from 0 to 1. When power factor is 1, that means theta V minus theta I is 0. What's the meaning of that? The load angle is, impedance angle is 0. That means load is resistive. In this case, P line is minimized. So the viewpoint of the transmission line, we need to make a PF1. So how can we make? Therefore, PF should be controlled as 1. How? That is the compensating impedance. I told you that the power factor is determined by only theta V minus theta I. So power factor is determined only the load angle here. So to modify the power factor, we need to modify the load, the impedance. So we can the compensating the impedance to change the zeta V minus zeta I go to the 0. So we call that is as compensating the impedance. So this is an example of the compensating the impedance. So we call the correcting power factor. So the meaning of that is the source here that we have one line impedance like that, and there are load. We have load here, this resistor, and the inductance looks like that. This is connected this way, so, and okay, and this is a line impedance, transmission line impedance. There's R1 and L1, and this is a load impedance. So in the viewpoint over here, this is R and L, and the load impedance is G, will be R plus J omega L. So if you draw this impedance in the composite plane, this is R and this is omega L, and this is a G. So this theta is a load angle, will be arctangent L omega L. Therefore, the power factor, in the case of only load impedances exist, then power factor PF will be cosine arctangent L omega L. This is a given power factor. This is a line load. So we want to change the power factor. How can we do that? Actually, we can't do that. We cannot do it. Why? The load is fixed. This is a fixed values, and L is fixed. Why? Load is fixed. For example, we want to operate the washing machine, or refrigerator, or elevator, and light, and whatever it is, we want to consume the electricity. Then the load is fixed. I do not want to operate our home appliance according to the CAPCO's the status. We want to use our appliance as you want. So that means we cannot control the load impedance R and L. So the power factor is determined by the load. That's it. But in the viewpoint of the transmission line operator, like CAPCO in Hanjin, they do not want to make a poor power factor. So they want to improve the power factor upward to 1. That is the maximum values of power factor. Why? High power factor cause low current in the line impedance. So we can add in some impedance here for the compensating the power vector. We call this a GC. So GC could be RC plus J XC. I don't know what is the XC. Actually, I don't know what is that. Anyway, it's XC. But the reason we insert the compensating impedance GC, this is a the reason we use the compensating impedance is improve the power factor. So we not want to consume the power caused by the compensating impedance. So we do not want to consume the energy. So this is 0. Therefore, the GC can be modeled as a XC. I don't know what is the G axis XC. So include this compensating impedance, this total impedance will be represented in this will be the parallel of compensating impedance and the load impedance. So that will be G plus GC, G and GC. So that will be P plus JXP, we define here. And there will be GP and set up in the polar forms. So including the compensating impedance, we call this is the new power vector we define as PFC is cosine theta P, because this is theta P. So there will be cosine arctangent P XP in this manner. So that means we design the XC, we can make a new power vector. There will be, and that means we need to correct the power vector, including the compensating the impedance. So to get a PFC, so we need to know what is the GP. So we calculate GP again here. GP will be G plus GC, G and GC. And G is R plus J omega. Actually, we read right here simply R plus JX. Like that. So there is X plus JXC and R plus JX and JXC. So it will be R square plus X plus XC square and minus X XC plus JR XC and R minus J X plus XC in this manner. So we need to simplify this. So that will be a little complicated. R square plus X plus XC squared and R XC squared plus J R XC squared plus X plus XC, X and XC. It looks very complicated. So we can read right here is r squared plus xc squared all xc squared plus j r squared plus xc squared xc all xc plus xc and x. So that will be Lp plus jxp. So we want to know the load angle include the compensating impedance. So we want to know angle is Lp xp, because this is Lp and this is xp, so that result is L xc r squared plus xc and x. So that will be tangent arc cosine PFC, and that will be derived based on these relations. So if we have the reference PFC, I mean, if we have designed, if we want to, if PFC is fixed, that means external fixed is desired. For example, chance 1, because 1 is the highest, the PFC values, the perfect values. So to make this desired PFC, we need to define the XC. So therefore, XC can be rearranged based on these equations. And from here, we can determine the XC is r squared plus x squared all tangent arc cosine PFC minus x. Because the cosine, here is cosine is even function. Therefore, according to leading or lagging, XC could be very low. Anyway, if you want to make up that PFC, then if you insert the compensating impedance XC in these values, then you can achieve the PFC values here. if axis is capacitive, then maybe S will be that value is that is all tangent cosine the desired PFC minus x and r square plus x square. And from here, omega c can be written. We arrange it based on this equation: r square plus x square and x minus r tangent cosine the desired PF values in this manner. So that will be r square plus x square and r and x over r minus tangent cosine PF's values in this manner. So let the theta is the load angle in the original load, tangent, arctangent, and Rx. And Rx is the original load, then omega c, that value is omega c, can be rearranged based on the theta is r square plus x square and r, and that is a tangent theta minus, this is a theta, right? You want to theta, this is tangent, and the collected angle is theta, that value here. So here is theta is the original power factors, and theta c is the desired power factor. So we can design the compensating impedance by capacitor to make a power factor angle is theta c. And so the visual tower line again. This impedance make angle theta c, equal loading load and compensating impedance. So the power factor is a move from the cosine theta to cosine theta c. So power factor changes from the cosine theta to cosine theta c. So we'll give a simple example here. Textbook example 11, 6, and 1. We have two loads. So one is a 50 kilowatt the resistor. Maybe this is a heater. And 100 kilo VA, that means and it is the apparent power, and 0.86 the lagging power factor. Because this is lagging, that means inductive the load, the power that will be motor drive. and then require the rated voltages is 10,000 volts. This is RMS values. Then determine the problem is determine total current and finds the overall the power factor. There's a questions. So it's very simple. I mean, actually, we don't care the line impedance in this problem. So anyway, we need to know what is the power factor in the given the system. So I mean, there are source here, and the source voltage will be provided to the load. There are two load here. I mean, one load and another load. So the given voltage is 10 kilovolt in RMS, and this is load 1. I mean, this is G1, and this is G2. The G1 consumes the power is 50 kilowatt. This is purely the effective value, I mean active power. And G2 consumes the 100 kilo VA. I mean they are lagging power. So we need to know that this is S1. This is S1, and because this is S2. So S1 is very simple, right? This is only P1. This is the 50 kilo. It's very simple. And the S2 is a little complicated. I mean, actually, S2 is lagging power. So in this case, this is the lagging power. Therefore, theta V minus theta I is theta 2. We define theta 2. That is a positive. So theta 2, actually, because the power factor is 0.86, that means power factor is determined by cosine theta V minus theta I. That is cosine theta 2 we define, that is theta 2 is 0.86, and theta 2 is positive. So theta 2 can be calculated arc cosine 0 point here. So that value is plus minus 30.7 degree. But because theta 2 is positive, there are only one values. What is that? Theta in 30.7 degree. Therefore, we can rewrite S is the magnitude is 100 kilos and angle is 30.7 degree. So that is 100 kilos cosine 30.7 degree plus J 100 kilos sine 30.7 degree. So that will be okay. So that will be 86 kilo plus J 51 kilo. So this is a P2 plus J Q2. So total power, total composite power is S1 plus S2. So 50 kilo plus 86 kilo plus J 51 kilo. So it will be 136 kilo plus 51 kilo. This is a P plus this is a Q. So that can be represented in the polar forms. 145.2 and angle is 20.6 degree. The unit of that is kilo VA. So we know that this is a load angle, so we can calculate the power factor is cosine 20.6 degree. So there will be 0.94, and that will be positive, so that means lagging power. Then we can calculate the current. I mean, because the operative power is half, actually, V magnitude and current magnitude, and V RMS and current RMS. So current RMS is okay. Is 145.2 kilo and divide by 10 kilo. So there will be 1.52 ampere RMS. So we can calculate the power factor and the current. It's very simple problems. And we have another example. That is an example of power factor correction. So using the compensating the impedance. So as an example 11.6 and 2. This example of power factor the correction. Yeah. We have a source and we have load here. Okay. We have a source here and we have a load. This is a G, and the G is the 100 plus J 100. So this maybe this is inductive, and this is inductive load. Then our target is in this case maybe what is the power factor? It can be represented here is 100 square and angle is 45 degree. Therefore, power factor of this is cosine 45. So maybe 0.707 will be power factor. If there are only the G, then power factor will be 0.77. This actually, and this is inductive, so lagging power factor. Then our target is, the problem is power factor 0.7 to 0. Actually I'm going to change the 0.95 lagging. How can do that? We can add in the other impedance here, like that. This is a GEC. So question is, how much we have adding the GEC to improve the power factor from 0.707 to 0.95. So we already know about that. How can you do that? That's your questions. That was we have to do it here. So you know that here. So theta is, here is theta is 45 degree, and our target is 0.95 should be cosine theta target in power angle. Therefore, theta C should be 5. So you need to make that values through the capacity, theta C. That value is 18.19 degree. It's very simple. So to do that, we know that R is, N. We know that R is 100. And 100 square plus X is 100. 1 square, and tangent theta is 0, is 1. Why? Theta is 45. 5 minus tangent point degree here. So the variable is tangent 45 is 1 minus tangent 18.19 is that varies. So .671 and 1/200. That is 3.36, and that varies here. The problem here, we have omega is 377 radian per second. That is maybe 60 hertz here. So from here we can calculate the C is 1/omega 3.36 10 minus that values. So Then result was 8.9, that varies. Unit is capacitor unit is farad. That will be 8.9 microfarad. So if you adding the capacitance is 8.9 microfarad here, it's like that. Then power factor, the moving from the 0.707 to 0.95. So if you make another example, if you want the power factor is not 0.95, if you want to target, you can change the targets. Copy. Another target is not 0.95, our target is 1. It's a perfect power factor. Then what can you do then? You can use the same procedures to get the omega c. So omega c will be all plus x squared all tangent theta minus tangent theta c. So when the power factor is 1, what's the meaning of that? I mean theta c, power factor is cosine theta c is 1. Therefore, theta c is 0. So there is 100. It's 100 squared plus 100 squared, and theta was 45. 45 degree minus tangent c is 0. So that is 1 minus 0. So from here, capacitor can be calculate 13.3 microfarad. If you're adding the 13.3 microfarad here and here, then power factor is perfectly 1. So this is a reason we use the compensating the impedance and how to design the compensating impedance to collect the power factor as you want. Okay. And this is another example. It's 11.6 and 3. So we calculate complex power on this problem. We have a circuit here, is that here, and voltages. We need to check this direction here, minus plus, and here, register here, and inductor like that. So we define this is a Vs, and this is a 3 ohms, and this 0.54 Heli, and define this is a VO. So in problem, they given the voltage is given VST is 7.28 cosine 40 plus 77 degree in volts, and the VOT is given it is 4.254 cosine 40 plus 311 degree. Actually, VO is not required because we can calculate VO through the circuit. But anyway, the problem give us the variables VO. It's very thankful. So we need to redraw this circuit with pager. I mean, to calculate this, simply paste, withdraw this again. Then that variable will be Vs will be 7.28 in 77 degree, and omega is 4, and this is 3. It's 3 ohm, and this is VO. VO will be written here. VO will be 4.254 and 311 degree, and J omega L is omega is 4, L is 0.054, so there will be J 2.12. So J 2.12. This is not important problem here. Anyway, and we define the current in here. We define current here in this way here. The current here. From here, because this current going through the inductor, so I can be calculate VO divide J 2.16. So there will be 4.254 in 311 degree, and divided by the J is 2.16 because J is 90 degree. It's like that. So there will be 1.969, and angle is 221 degree. It's ampere here. So at first we can calculate the average power supplied by voltage source. To do that, we need to calculate S of the source. Will be half VI conjugate, and because our direction of the current is going to the positive polarity, so this is because this is a passive convention. Why? Because the direction of current is determined in this way. So anyway, that will be half. The voltage is that values, so 7.28 and 77 degree, and current conjugate is 1.969, and the conjugate minus 221, because this is the conjugate. So the variable is 7.167, and phase angle is 77 minus 221 will be 7.167, angle is minus 144 degree. Therefore, 7.167 cosine minus 144 degree plus J 7.167 and sine minus 144 degree. So this is very simple. So you can calculate their variables. is minus 5.8, and you can do that is plus J minus 4.21. So minus 5.8 minus J 4.21. This is active power P, and this is leak power Q. So because we use the passive conventions, the minus value means the 5.8 watt is supply input is supplied by source. Next is the B. Next problem is average power received by the register. So we know that based on the calculation, actually we know some values over here. Here. So based on these results, we know that the 5.8 plus J 4.21, this amount is supplied through this source. So this is power, active power. That means that register will be consumed 5.8 watt, and this reactive component inductor will be consumed 4.21, the VAR var. So what into that is define this as a VR, and current is this direction here. So SR is half VRI. The VR is RI, R3, and current is here is 1.969 and 221 degree here. So that will be 5.907 to 1. So adding here the values is half, this conjugate is 5.907 to 1 degree, and current is 1.919, and actually 996. This is 969, and current minus 221 degree. So the value is 5.8 into 0. So there is 5.8. So there are only P, the no Q. So now this is a source supplied by the source, then 5.8 consumed by register. So the average power received by register is 5.8 watt. Then the problem is C is the average power received by inductor. The same way, we can calculate the SL is half VL is VO here is I. Is half VO was written in this way here, 4.2. VL is 4.254. This is a conjugate. In English is 311. and current is 1.969 minus 221. So the result is very simple. And the result is 4.21 angle is 90 degree. So 4.21 cosine 9 degree plus J 4.21 sine 9 degree. So that will be J 4.21. So there are only Q. So active power is 0 and the Q is 4.21 VAR. So supply from the source is consumed by the inductor in their variables. The last is the power factor. In this problem. So power factor is can be represented here. I mean there are voltages and inductors. So we can define that variable. We need to know that V, and we need to know this current. The problem is the voltage is given 7.28 and 77 degree, but the direction is this is positive and negative. So we need to change this V is written in the magnitude is the same is 7.28, but the angle is reversed. The voltage angle is reversed there, so there will be original value is 77 and reversed means 1 and 180. So there will be 7.28 angle is 257. So we know the theta V is 257 degree, and I know the current was 1.969 and it is minus 221. Actually not. This is positive. I mean, this is 221. We can calculate that value from here. So theta I is 221. So power factor was cosine theta V minus theta I. So cosine 257 minus 221 is 0.809. This is a power factor, this problem.